Okay, so welcome from my side. I hope that all of you can hear me and see my screen. Please let me know if that is not the case. I'm not the super Zoom expert yet, but I think it will work. So first of all, thanks for joining this workshop. And before we dive into details, maybe a few words to my person. Maybe some of you know me already, others probably won't. So my name is Sebastian. I work here in Germany, in Munich, for Zeiss Microscopy in our software department. And I'm mainly responsible for our AI solutions, but also our Cset file format, which probably one or the other has to deal with all the time. And today in that workshop, the idea would be to showcase a bit 3 different Python packages we developed at Zeiss first internally, and based on certain requirements, which I will talk about a little bit later. But then we decided, obviously, it would also make sense to make them public. So basically publish them on PyPy, as some of you do as well, so that the community can make use of those and develop new tools, maybe find some issues that we didn't spot and give us feedback on what could be improved. Basically, make it a useful tool for everybody, and don't keep it, let's say, in-house. So during this workshop, feel free to say something at any time. Just grab the microphone and ask questions. So I have planned basically 4 different little topics which I want to cover. The first one would be talking a bit our motivation, and then jumping into the first Python package, the Cset package. And I'm not sure, in the workshop page, there was this kind of like pre-workshop information. You should have found the 2 links for 2 different GitHub repositories. So one is here, this one, I2K 2022 Zeiss, and the other one, I think it's called Napari Cset ANN segment. And basically, if you have those GitHub repositories open, especially for the Python packages, you will find most of the information here. And when it comes to the interactive part, clicking around inside the Jupyter notebook, I hope it will work. You can just use the link for the Colab notebook, or if you prefer, it's a bit up to you. Obviously, clone the repository and run the Jupyter notebook locally. But for the sake of that, it should run, and we don't have to deal with those, oh, I have not installed X. We decided to also integrate those Colab notebooks, so we can be more or less sure it will work. So so let's start, unless there are already some questions. If there are questions, just speak up and I will try to answer them all. So as I said, Cset will be the first one I want to cover. Then a package called pylib Cset read write. Then Cset model, and maybe a little bit as a bonus, let's see if we can make it run for all of you. There's always a little bit with like, how is your environment? I will also showcase a still experimental Napari plugin, which is using some of those packages to segment an image using a deep neural network that was trained beforehand. And maybe here at that point, I will 1 or 2 times jump out of this GitHub repository or out of the notebook, and maybe for a few minutes show you some parts of our Zen or Appear software. Here you can just, I would say, see what I'm doing and keep asking questions. Okay, so good so far. Let's start. So maybe a bit the motivation. So as probably most of you know, at Zeiss, we are not only making microscopes. This is not so much my business anymore. Used to be, but not anymore. Now I'm more into software. And in our software platform, we have Zen Blue, Zen Core, we have Arrivis Vision 4D and some other stuff, not so much of interest for you. All of those software platforms have nowadays some built-in AI functionality. Deep neural networks are used for segmentation, for image classification, for image processing. So, and since our team is a bit responsible for the overall machine learning infrastructure in our software, we always encountered this problem that all the different teams had the tendency to develop their own tiling of images over and over again. And this is, depending obviously from your personal opinion, not so much fun. For sure, it's not super efficient. And in the end, also hard to maintain if every project develops its own tiling algorithm, which is especially the case for those machine learning stuff, because images are too big to be processed at once. So, and here we decided, especially with respect to AI, so what's a good idea? Let's develop a little internal Python package first, where we define our tiling algorithm that is useful for most cases, and then publish it internally. So every team can do at Zeiss internally pip install Cset tile. And then we decided, let's make it public. So, and what we are going to do now is we follow that link here, click on Cset tile, and it will or should bring you directly to the Python package index page of that package here. I hope that works for most of you. And now what we will do, maybe talk a bit about it. What's this package capable of, what it can do, also what it cannot do. And then we will jump into the Colab notebook. So let's have a short look. So here you see some information. Here also the guy who finally pressed the button, a colleague of mine, Nuno. Basically, it's like every other Python package. Internally, it works like this. If we create a new version of our Cset tile package in our environment, it automatically pushes a new version to PyPy. So, and here it's basically the description. This is containing the most important information. So yes, it's called Cset tile, Python package to simplify the process of tiling arrays. And already from that line, it should be clear, it's explained here as well. It's not tied in any way to our Cset image format. So it's a package to simplify the process of tiling arrays. Where this array comes from, doesn't really matter. In our case, obviously at Zeiss, the arrays in Python are typically come from Cset images. But probably in your case, that might be something else as well. So it's not tied to the Cset image format. Nevertheless, somebody decided, let's call it Cset tile for Carl Zeiss tile. Not super creative, but I think it's okay. So, and yeah, it's pure Python, so nothing fancy behind it. And in principle, the most important topic here is the tiling strategy that we implemented here. And yeah, also here, based on our long discussions, what should be a good name? We try to be, let's say, keep it a bit technical and called this strategy, we implemented almost equal border fixed total area strategy. It's a bit long, nevertheless, this is what the developers voted for, and that's fine with me. So basically, the idea is that you have an array. And for instance, let's say you want to train a deep neural network, and then you have to always decide like how much overlap should there be between tiles. Is 5 pixels okay? Does it have to be 10 pixels, 100, 200, 500? There is no one value that works. And especially at Zeiss, we encounter a lot of images, not only from the bioimage community, but also images with way larger structures in it. So in my opinion, the tiled overlap you need for AI applications really depends on what are you actually, for instance, segmenting. So if you know how big your objects typically are, you have a more or less good estimate what tiling is needed. And yeah, here is a bit of an explanation. So there are some assumptions. So image area is completely covered by type and is filled up with few tiles as possible. This is what we want to achieve. And then the overlap between the tiles obviously should be as small as possible in order not to create really a lot of tiles. But we must make sure that a minimum border size is used for every tile. This is what I just mentioned. So, and interior tiles should have all the same size. And then like a possible excess, because depending on tile size and overlap, it doesn't really always add up to even numbers so that it exactly fits. There might be tiles that have slightly different size at the edges of your big image. Nevertheless, the overlap always stays the same. And yeah, there are some more considerations. So this is what we started with. And basically, we try to come up with an illustration of what this all means. Feel free to give some honest feedback if this is easy to understand or not. But here it's basically, it contains all the important terms. So border width, left and right border, minimum border width, so on and so forth. I think it will become a lot clearer if we click through the notebook. What we also integrated here as documentation is basically a little bit more formula-based explanation. So what we did set up those requirements, and then somebody in our team smarter than me came up with all those formulas. So what does it actually mean? This here is exactly the same, what I described in words, but as formulas. I don't have to read this here, but basically there are 3 cases. In principle, use a single tile with no borders if your tile size is exactly the image size. If it's the other way around, then it doesn't really make any sense. And then this is the normal use case. You have a large image. You need to train your network with, I don't know, 1024 by 1024. And you need an overlap of 100 pixels. If you have this as an input, this logic here can be used to create a tiling strategy. So, and I would say now it's time to jump into the Colab notebook, unless there are already a few questions. I'm not so sure. Wait, can I see the chat here? Yeah. Oh, there's a question already. Does Cset tile support ND images? So currently, as you can read from the name of the strategy, it's 2D tiling strategy. This is mainly because this is what we currently do, but it could be pretty soon that we extend it to 3D. So the same logic would apply to 3D, but we didn't implement this one yet. Also a bit based on feedback. My gut feeling is we will do this pretty soon. So as of today, it's like to tile 2D arrays, but in principle, it would work also for more than 2 dimensions. Okay, so let's here now jump into Colab. Or as I said, please feel free to clone the repository. So now I just assume that most of you are familiar with Jupyter notebooks and Colab notebooks, at least to a certain extent. So Cset tile itself, as I said, is pure Python. It doesn't have a lot of dependencies. So installing it should be more or less straightforward. And to make sure it's correctly installed in this Colab notebook, here we just will execute that cell at the very beginning, upgrade pip, and then obviously install Cset tile. And here are some other libraries because I have to do some plotting and illustrations down the road here. So let's press this button here and wait for the installation. Shouldn't take too long to install it. And here I must say, really, Colab is really nice because you can more or less make sure it works all the time. So installation went fine. So, and now, let's go step by step a bit through how is this package being used. It will also be used in the other Colab notebooks later on to a certain degree. So there will be a couple of examples. So first of all, here, this is normal importing stuff. And as I said, this is what we are going to use here from seize the tile, fix total area strategy, import. This is our tiling strategy. And then also we import, so to say, a rectangle object, because a tile is in our world basically a rectangle with a certain width and height and so on and so forth. So this is the normal imports, shouldn't be too tricky to use. So as hopefully most of you know, Zeiss has its own GitHub page. Here you see it here in the link. If you go to GitHub and type in Zeiss OED, there is a Zeiss OED GitHub page, and this contains also some Jupyter notebook and some data. And inside that Colab notebook here, we will basically download some of the data from that repository. Obviously, later on, you can try it out with your own data, but here you can basically just execute this cell, and it will set the path to our Zeiss GitHub repository. Just for fun here, Zeiss OED GitHub. It's basically that repository here. It contains a lot of different stuff, from microscope to automation to machine learning to other things. And in our case, also here's some data somewhere in here, which we will use. But feel free also to use stuff on that general GitHub repository. Okay, so we did set the correct link to the data. And now we need to download the data basically for that Colab notebook. And therefore we have this request library, and here we basically check if the data are already existing locally, if you run it as a normal Jupyter notebook or not, and execute it. Okay, went pretty fast. Basically, it contains some images of fluorescent cell nuclei. It's not super fancy. So here we did read the images. I think it was done by scikit.io. It's the PNG file, so very straightforward. Okay, let's have a look about the shape of the image. So here you see it's a very simple 2D array. The width, almost 2000 pixels. Pixel height is like 1416. So nothing fancy. And and here, obviously, I will not in this notebook apply it to AI processing as well, but in order to have some kind of processing function that we can apply tile by tile, I just create here my own as an example. And in this case, I decided to use a very simple Gaussian filter, which I defined here. Obviously, later on, if you apply a deep neural network, this processing function will be the prediction for an individual tile. But here in this notebook, we try to keep it as simple as possible. Okay, so this is a simple function, but feel free, obviously, to modify it a bit and use your own. Here, basically, input is an array and some kind of parameters. In case of the the Gaussian function, yeah, it will be the sigma, but could be something else if it's a different filter. Okay, let's execute it. So function is basically defined. So now here, this is where now our tiling package comes into play. So in this cell, we basically create a so-called tiler object or tiling strategy by calling that tiling strategy we discussed and specifying what is the desired dimension of the tile I want to have. And you see here, it doesn't have to be square. It can be a rectangle. And here I decided to choose a minimum border width of 128 pixels. Just for fun. You can always play around with that one. And if we now here want to create the individual tiles, then we use that call here. Basically, yeah, put in the image that we have and see what the tiles will look like. And to give you an impression, I just will print those tiles or dimensions. So it's not already creating tiles. It's basically just the coordinates of the tiles. So always like top left and then width and height. So in that case, our image of 2000 by 1400 will be splitted into 4 individual tiles based on those parameters. If you use other numbers here, you will get probably more or less tiles. That's already it. And now here, if you have that one, those tiles that you can basically iterate over, you can use to extract parts of your array. Imagine you have a big array, all you have to do is like go through your tiles, and for every tile you have now the positions of the tile, and that you basically use to cut out stuff from your array, and then you can do whatever processing you want. And this is exactly what we are going to do now. So here, just for fun, we will create some plots. And here you basically see what we are going to do now. So we loop over those tiles, in our case, 4 of them. And here we use basically the information from every tile to cut out part of the image. So this image 2D, it's the bigger image. And then for every tile, we cut out some stuff. And then we basically do the processing by calling the function process2D. Input will be the current tile. And here as an argument, that makes sense because we have the Gaussian filter here, we put in here sigma. Okay, and then here, obviously, I just do a little bit of, yeah, basically displaying. Let's see what it looks like. So here you see it was processing 4 tiles. And here you see always, okay, that was cut out of the first tile. That is the first tile process after the Gaussian filter was applied. Second tile, processed version of it. Third tile, fourth tile. I think this is more or less straightforward. And obviously what we do here is we basically put in the process tile back into a bigger one. So at the end, we can basically compare the original complete image with the processed image tile-wise. So keep in mind here, this is our image. Tiling. So basically, just to recap, here we define the tiling strategy and then the parameters. Then we basically put in and use the function tile rectangle. And yeah, what is a rectangle? You have to put in a rectangle. So and then here you use yeah, what you already have from your image. And then you have basically all your tiles ready as something you can iterate over. That's basically already it. So and the last step here is maybe to visualize the results a bit more nicely. So basically by plotting the original image and the processed image and also the tiles. I think here I'm not going into the details of the plotting because I'm not a super expert here, but basically here it's a bit outlining what is happening. Here it's basically the first tile. And you see here at 1200 pixels, 1000 pixels. Here you see the same tile in the processed image. And basically here it's plotting all 4 tiles. So in the end, it adds up together. And you have those 4 tiles. And we did make sure that all the time there was at least an overlap of 128 pixels. Please feel free to play around. Yeah, see what you can do with it. But this is more or less, I would say, already it. Basically, there is a unified tiling algorithm that we at Zeiss use now wherever possible, so in different software platforms, because it ensures, in my opinion, that first of all, nobody is wasting their time by developing it over and over again. It's easy to install, pip install. At Zeiss, we also have a .NET version of that, obviously. But depending what part of the software we are talking about, it's either installed by pip install Cset tile or as a NuGet package, not so much of interest for you today. And then we use it internally in all of our machine learning workflows. And by using the same tiling in different parts of the software, we also minimize those artifacts that probably most of you know. Because if I use a different tiling than you, depending on the size of the objects, the effects you have to deal with will be different. And this is always tricky. So having a unified tiling strategy at Zeiss turned out to be very beneficial in our software development. And therefore, we decided it also might be beneficial for some other people. Let's publish it. And this is what we did. Okay, so that would be it from the Cset tile library. Are there, okay, there's a tile merger planned. Good question. So currently, the library is only basically creating tiles for you. And how you put the image back together once you have the processed tiles, obviously, is up to you. So that means, obviously, we do have different ways of merging tiles, especially when it comes to deep learning applications. Here in this example, I just didn't use any fancy functions. I just put it back into the bigger array. So it depends. Currently, we will focus on this tiling thing. If at some point we come to the conclusion that also our, let's say, tile fusion functions should be made public, at least we will consider it. But right now, there's nothing public that we use internally. Yes, we have some stuff in the makings. So let's see how it develops. Okay. Yeah, also here, data, sample data are there. Feel free to use it. And yeah, give me feedback how this can be yeah, improved or maybe adapted. And I would be really interested to learn if one or the other person of you will actually use it at some point. It's not rocket science, but it's just, you know, it works, in my opinion, quite nicely and saves you some time. Okay, so yeah, then I would say let's close this one and go back to our, oh, now I have to find my, the correct page. Where is it? Cset tile, here, PyLib Cset I read right. Okay, so the next thing I'm going to talk about is PyLib Cset I read write. yet another Python package was published a bit earlier, I think, or was it? But only a few days. So now I'm talking about a tool to read and write CZI images. So before we dive into the Colab notebook again, let's talk a bit about what does it do, what's the motivation for that one. So as probably some of you know, reading a CZI actually can be done in different ways outside of our Zen software. Probably the most popular way is using bioformats. CZI is an open data format. So if you go to our webpage, search for CZI, you can register, and then you will get a download link, and you get some examples and also the internal specification of the CZI file format. So everybody can have a look here. And based upon that specification, Bioformats has developed already years ago, also with some support of us, a component called CZI Reader internally. But as all of you know, Bioformats it's based on Java, and this is really useful, and it's still used all over the place. But internally at Zeiss, we do have some projects where we also need other ways to read a CZI. And I think 3 or 4 years ago, we first published on GitHub a C++ library called libczi. Libczi, as I said, C++ library to read CZI images. And back then, I started already discussing with our managers, shouldn't we also, first of all, create then an interface in Python to read CZIs directly and also allow people to write it? And yeah, it took me a little bit of time to convince everybody. But what we did now, we published an update here for the libczi C++ library, which is called libczi read-write. Will be soon on GitHub. As of today, we didn't have enough time, because you can imagine a bigger company, if you publish something on GitHub, you have to fill in many documents. It's not just checking in your changes and say publish repository. It's a bit more complicated, especially in the first place. So, but now we did a fundamental change of strategy here, because now we also officially allow everybody to write CZIs. Not only reading, that was always allowed, now it's writing. And based on this C++ library, again, we said, okay, wait a second, we have a lot of teams developing all kinds of algorithms. If we're talking about AI algorithms, which is my main field of responsibility, we are mainly working in Python, not in C++. And then it's again the same thing. Every team always had this, okay, what's the best way to read a CZI in Python? And luckily, some people from the community already picked up the earlier libczi and created, for instance, the IX PyLibczi, the people from the Alan Cell Institute. But also, probably you know him, Christoph Golke, basically used our CZI specification directly and implemented his version of reading CZIs. And I must say both packages are excellent. Nevertheless, none of them can write CZIs because mainly it was not allowed, and also are a bit, have some little drawbacks. For instance, the one is really focused on something called the subblock interface, which is nice but complicated. And the other one could not really easily read parts of a CZI. You can imagine if you have a large Cset stack, a long time series, or even a large 2D image, what you want is a function to easily read parts of the image. And therefore we decided, okay, if many of our development teams have the issue of reading and writing CZIs from Python all the time, because obviously we have an image in our Zen software, then you want to read it to do some AI processing, and then you want to write it again as a CZI, so it works in our software seamlessly. But also outside, storing multidimensional large image data in a CZI is not a bad idea. Give it a thought, especially if you want to use it in our image analysis tools for our databases or whatsoever. So, but basically, PyLibCZI read-write now is a Python wrapper for the libCZI read-write C++ library. It's really focused in its current form on simplicity. So there could be many more things and different forms of APIs. It's just one of the first releases. So more is here to come, but we try to keep it simple. So, and what is important is it's focusing on reading and writing 2D image planes. And I think you will see this in a second when we jump into the notebook again. Installing is straightforward. Pip install PyLibCZI read-write. As of today, we do not provide wheels for Mac OS, but that will probably change soon. We just didn't have time to do it. So people already pointed that out. I totally get it. Yeah, so stay a bit patient. And I already saw your question with respect to the metadata. You can write some metadata, not all of them, because pinhole size, zoom, etc. It wouldn't be hard technically, but our approach was, let's first start with really a few metadata that are really required, because pinhole size, zoom, and now it gets a bit technical, are not strictly speaking necessary metadata for a CZI image file. Those are hardware related data. If you have an LSM, obviously pinhole makes sense. If the CZI comes from a wide field microscope, then it does not. And therefore, in its current form, the newly created CZI and the current interface does not allow you to write all kind of parameters that you can think of. What we already started talking about is allowing to write your own custom parameters that are specific for your processing applications in this custom attribute field. But please feel free here to give me as much feedback as you want. Also on ImageSC, what is your use case? What would you like to see? And I will promise we will have a close look. We're probably not going to do everything, but let's see. So let's start the Colab notebook. And yeah, so here's a bit of explanation. So I think this I already mentioned, and I think we can jump right into what's going on here. So first, obviously, let's do the import. Oops, sorry, I have to obviously probably start here at the beginning. So run anyway. And here you see it's installing PyLibCZI and also the CZI library, because there is an example using the tiling. You will see it at the very end. Okay, that worked. Nice. So yeah, first the import, not too fancy. Here from PyLibCZI read-write, import CZI as, I called it PyCZI. Yeah, and here some other libraries that we will, on packages we will use later on. And here you see it's the same logic. Yes, to have some example data, so to say, we place them on our GitHub repository so that you can have access directly from within that Colab notebook. So basically you can run it right away and you don't have to download anything. all works more or less automatically. Okay, so here again, download the stuff. What is now? libc.I data zip. So, oh, I forgot to execute the cell probably. Ah, now it works. Okay, so, and now we will go step by step through some of the functionalities. Obviously, the most common task is opening a Cset. And here we strongly recommend using a context manager. So with Cset, file path as Cset. This will open the Cset in read-only mode. Here is an example. So in the sample data, there should be, let's see, data, here, inputs, sample data. Here, there are some images. And now we can use them. So the first thing I will do now is here, I will open this 5-dimensional stack. It's a time series, short one with a couple of Z planes and 2 channels, which I acquired a long time ago during a demonstration from one of our microscope. And the first task here is just read out all the metadata as in XML. Very simple and straightforward. And here now you will see this is all the metadata that are part of a Cset, and this is a lot. And I have to move this here a bit to scroll down. And we are not going obviously now to read through all of that. Just to give a little bit of impression of what you can now do based on what you actually want to read. Obviously, probably you would be interested in stuff like scaling and what's the number of time points and so on and so forth. You can obviously always extract parts of the dictionary. Having that said, I might, or we might publish a little bit an experimental Python package as well, which basically will create, or will be a bit more user-friendly in the sense of give me a Cset image, and then it gives you a scaling object or a dimension object. Basically, you don't have to dig through all that stuff on your own. But this is basically what the clear, nice, pure interface is. In the first place, gives you the metadata. You can also get the metadata directly as a dictionary, which might be a bit more user-friendly, depending on your taste. So that would be this one here. With Cset, open Cset, and here I used a different Cset with the scenes. And here I have the complete metadata dictionary. And now obviously, yeah, you can read out parts of it. Here in that case, I was reading out some other stuff from which is only holding information about the image. There's much more. There's typically information, then hardware settings and software information and those kinds of stuff. You can all read it up. But keep in mind here, Cset doc, metadata, that will give you a dictionary. And then you can do with the dictionary whatever you like. So next thing, obviously image dimensions. This is probably in most cases what people want to know right away. So how big is my image? How many time points do I have? How many Z planes? For that, we have a special function, and this function here is called total bounding box, and it's giving us all the dimension of orthogonal planes in the Cset file. So basically the dimensions of every dimension that is there. And there can be much more than time and channel and set. There could be illumination angle and phase and whatsoever. This is why the normal, let's say, ohm set of dimensions is not sufficient for for some of our devices, and also one reason why there is still always a bit the need for different file formats. But that's a different discussion. So let's try it out. Again, we use the context manager with pi czi open as czi doc. And in this case, now we ask for the total bounding box. And here we just print it out. And here now you see the results. So it has a t dimension. And that is the range you have. So basically it has 3 different time points. And it has a z dimension, it has a c dimension, it has a b dimension. That's the block index. It has only one block. Block is basically in Zen, there is something called multi-block image acquisition. There is only one. Some images have it, others do not. Yeah, and here X and Y. And remember here, if you go back, or here you see it, sorry, I don't have to scroll. Here it's basically from that image. T equals 3, Z equals 5, 2 channels, and yeah. Okay, let us see total bounding box. And here you can extract all the information you need. What you can also extract, and here I take the image with the different scenes. So scenes are basically physically separated positions where you acquired an image. Let's assume you drive with your stage to position A, you acquire an image or even a tile image at that first position, and then you drive with your stage physically to another place, and again you acquire an image. Then this is what we call it in our software scenes. So really physically separated regions, but all stored in one CZI. In this case, obviously, total bounding rectangle, what is it? Gives us the X and Y dimensions of the complete CZI. And you see here, this is like, width is really big, height is rather normal, small. So that means you will see it later on. Basically, 2 positions that are physically separated. But this is the overall total bounding rectangle. So the rectangle that contains all the scenes from your image. Also, very straightforward to use, nothing fancy about it. And now here, obviously, you can have the bounding rectangle of individual scenes. Therefore, we have here another option, CZI doc, and then scenes bounding rectangle. Let's see how this looks. And here now you see it's a dictionary because, as I said, the image has 2 scenes. It's that one here. It's from a 90 well plate, and there is one image in the first well and one in the second well. And here now you see, okay, it has 2 scenes. And for the first scene, the rectangle is 0, 0 as a starting point, and this is the width and the height of that scene. So it's, I think, one camera frame, if I remember correctly. So very simple. And then obviously there is a second one. And here the starting position is different. You see it's not only moved to the right, it also is a bit moved in the Y direction. Most likely, this is because if you put in a well plate in a microscope, it's never 100% perfectly aligned to the XY driving direction of your stage due to imperfections in the material, a little bit dirt, whatsoever. But here now you have basically a dictionary containing the 2 scenes and the dimensions of that. And now if you, for instance, want to read the first scene, I think it already becomes quite clear what you can do. You just have to read out, okay, I want to read the second scene. Where do I find the image, the pixel data? Then I have to take that information. We come to that in a second. Okay. Also, I think a useful tool is, or function is, obviously to check the pixel type. In case you want to do some processing, very often you need to know what the pixel type is. Same logic again, you open the CZI for reading with the context manager, and then you can get the pixel type. per channel. Here it's gray 16. And I say per channel because technically a CZI allows channels with different pixel types. This is normally a not so common use case, but imagine you have processing functions where you concatenate different images, maybe from different modalities. And it might not be always the best idea to always use the same pixel type for every channel. So at least CZI technically allows to have different pixel type for different channels. This is why you have to give a number. Or you use the function pixel types, then you will get a dictionary with all the pixel types for the existing channels. And here it's a 2-channel image, and as in most cases, both channels have the same pixel type. This is basically it. Also not super complicated to use. Yeah, now it gets a bit more interesting, reading the pixel data. So in a CZI, the shape of an array that you get in return when you want to read pixel data will depend on the pixel type. So either we have grayscale, or we have internally we use BGR. I forgot what the reason for that was. It had something to do with .NET and the fast access of access, so on and so forth. That's not the point. So either I just call it now BGR or RGB, I mean the same. So if that is the case, the returning array will have the dimension Y, X, and 3, claiming the pixel type. So this is important to understand. For a CZI, if it's an RGB or image, we don't have 3 channels. It has the pixel type RGB. It's 1 channel. If it's a grayscale, it's a bit easier. Then the dimensions you will get is Y, X, 1. And obviously, just by checking what it is, you always know what you have. There is a bit more explanations here with the background pixel determines the pixel value for the background, because you might have an image with where there are regions with no data. Let's assume you have basically a tile region which is tilted. So then, or something like a donut. There will be regions where there are no data, and then it has a background color. And the background color obviously must fit to the pixel type. So for RGB images with empty regions, the background color has to have the same pixel type. And if it's a grayscale image, the same applies. I wouldn't worry about this too much in the beginning, and rather let's focus on now reading a whole 2D plane. So yeah, if you want to read now pixel data from a CZI, it's crucial that it's clear that we're talking here now about plane-wise reading. So what do I mean with plane-wise reading? That means whatever you do, you will get back a 2D array, either with that shape for a grayscale image, or with that shape if it's an RGB image. And now, obviously, you will ask yourself, oh, wait a second, now I have a multi-dimensional stack here, time points, set planes, whatsoever. How do I specify which one of those do I get? And therefore, there is this plane parameter as an argument, and this itself, it's a dictionary. For instance, here, C0, Z2, T1 will read a 2D image plane from channel index 0, Z plane index 2, T time point index 1. If you don't specify it, obviously it will use like the first one from all available dimensions. This is what I mean by plane-wise reading. Whatever you do, it will give you a 2D plane. And now, depending on your application, you can all easily create a function which will read out maybe the complete set stack per time point, or I don't know what you need. So how does it look like? So here's a very first simple example. I define, just for fun, 2 different planes here. So first channel, set is 2, t gleich 1, and here just for fun, just some other index. Okay, and then I read the first frame. Here I do not use the plain argument, and this will be equal to this one here. Here we check the shape just to see if it's really grayscale or not for fun. And now here I read two other frames, and here now I specify the plain parameter. So keyword is plain equals this dictionary or the other one. Let's press the button and see how it looks. So here that is the first image. That is basically this one here. Frame 1 here, that is this one. And you clearly see this is a different time point. It was a live cell division, if you are interested, in 2 channels here. And yeah, that's the different channel, frame 2. That's already it. So by specifying the plane, you can read out a 2D array from the position you are interested in. And with position, I mean like with respect to all the indices that are available. Okay, so and now this is a small image. Yes, you can read the complete frame. So and now, especially also from the focus that our team has, AI processing, in many cases, this is like really small. Typically images, even from a normal camera, are, let's say, 3000 by 2000 pixels. And then now if you want to apply later on some neural network to it, then it doesn't really help to read the complete frame. You need parts of it. Or imagine this is a bigger image even. And therefore now you can also read parts of that specific plane by passing an ROI. And an ROI is written here, is defined as a tuple with the following parameters: X, Y, width, and height. And I think here now you can already a little bit start to understand why this makes later on sense together with the Cset tile library, because this is exactly what Cset tile as an example would give you, but you can define your own. And here's an example. So I define my region of interest, and then I read from my image this specific ROI for the first channel and for the second one. Let's see how it looks. That's now a different image, obviously here from this well plate. The original image has a much bigger dimension, but here you see 600, 800. And the starting points. So key message here is, from every 2D plane, you can also only read a part by providing an ROI. How do you get this ROI? Obviously, this is up to you. Feel free, obviously, to use the Cset tile library for tile-wise processing, but it can be anything. So, and then obviously you can also read, can combine this with specific scenes, because here I was just reading it from the default scene 0, and here I do basically the same. So I read stuff from scenes. First scene, second scene. So there is not only the ROI argument, you can have an additional argument which is called scene. For instance, if you now have a 96 well plate, what you can do is, this is, by the way, here the original image where I also cut it out, that stuff. Imagine you have a 96 well plate. What you can easily do, you can easily write a little loop where you read from the first well, you do all your processing. Then you read from the second well by just iterating over the scenes. So you never have to read the complete image. You only read what you want and what your processing pipeline can digest. If you want, obviously, you can also try to read all at once, or you can maybe come up with some fancy ways of using Dask or so. This is really up to you. But the CZI or the PyLib CZI read-write allows you to read only what you need. One way to do it is using the ROI. The other one is the scene parameter. Okay, so now let's move on, make it a bit more, more fancy. So there are additional parameters. For instance, what you can also do is you can provide another parameter called pixel type. What is this for? If you specify pixel type, then already by reading, the returned array will have the specified pixel type. So it will do a conversion. This will be done by libc_zi read-write on the C++ level. So if you already know that you need only, I don't know, gray 8 or whatsoever, feel free to already do this when you read. Here's an example. And you see here, I read always the same image, but in the end here, the output shape is always the same, but the pixel type is now different. So here it's uint8, float 32, or uint60. That's basically it. Also, I think quite interesting and can be really useful if you really know what you want to achieve. For instance, maybe if you work in a facility and a user comes to you and says, I want to segment X, and you ask him, okay, what is the resolution you actually need to segment this sufficiently well enough, whatever, and so on and so forth. It's not always the best idea to operate on the highest resolution level of an image. And therefore, we have a parameter called zoom. You can specify between 0 and 1. And this can be used to read out an image and basically scale it. So for instance, if you decide I want full resolution, you don't have to specify, that's the default. But if you want to have only like a fourth of the resolution, so it would be a bit like on a camera doing a binning of 4, then you can specify it directly during reading, and then only you will get a lot smaller array back. So here, for instance, I specify 2 different zoom factors, 1 original size, and here like a quarter. So basically here, then you can read a certain channel, a certain ROI, a certain scene, a pixel type, and zoom factor. And here, different zoom factor. So let's see what it does. And here you see now, this is the output, the shape. And here you see, this is zoom level 1. This is zoom level 0.25. And I think, or I hope you can also see it here during the screencast. Here, this is full resolution. This is downsampled. And I could argue that to do a segmentation, at least depending on the application, this maybe is sufficient. And then processing will be a lot faster. So this is why we have the zoom. What you cannot do is you cannot put in zoom factor of bigger than 1. So there is no upsampling because we didn't see a use case for that. And probably if you, I don't know, to be honest, if there is really a lower limit, there is probably for sure like 0.00 whatsoever. Okay, I see that question. Can it read the pyramid representation? No, it cannot. Also, because in pyramids, I know what you mean. The CZI has image pyramids right now. It's not directly this pyramid. So you cannot say, give me pyramid level 3. This is something we discussed. As I said, for the first version, we didn't really, we decided not to implement it. But if you have, you say it would be super great, Jean-Yves, okay, good to know. Okay, point taken. In the end, it's about like in what amount of time we can do what. but imagine you, also in Zen, pyramid levels are either going with a factor of 2 or 3. So it would be quite easy to basically achieve the same thing here. If you have here the zoom, you will get the output, but you are right, this axis is a point. So yeah, okay, I will think about it. Okay, so this is basically most of the stuff that is there for reading right now. And now we come to the writing part. This is entirely new because until recently, our managers basically were very skeptical about letting other people write CZIs. But in my opinion, times are changing. And we basically, what we decided is based on what I mentioned in the beginning. We use this library, pylib heavily internally to read and write CZI files. And therefore, I think it doesn't really make sense to say, but other people are not allowed to write CZI files, because it doesn't have so many options. If you write a CZI file and you open it in Zen, then you are fine. If it doesn't open, then you probably did something wrong. There will be a checking tool soon. But what it allows you is to create CZI files, store data in a CZI format in order to use it in other tools you might have and that you hopefully like, where it is important that it is a CZI. For instance, one example, we have a software called Core, which basically is a workflow software where you can create your own Docker containers for your processing functions. And in the beginning, we said, oh, a Docker container as an input, it can have everything. As an output, it can have everything. And this sounds intriguing, but in the end, in specific workflows, like really using the same specified file format all the time saves so much time versus supporting all kind of file formats. So from our perspective, writing CZI files saves us a lot of time, because now we have a NumPy array. What do we do with it? Do we save it as a TIFF? No, that doesn't make sense for us. Save it as a PNG, same thing, also doesn't make sense. So why not save it as a CZI? This is how it basically started. So now you can write CZI and create new ones. And the same logic as for reading applies for writing with respect to the plane. So what you can do is now you can write a CZI image plane by plane. You will see it in a second. So here now I will extract from scikit image just an image from the sample data. In order to have some array data, whatever that is. So you don't have to read a CZI to write a CZI. You can get the pixels from wherever you like. So first I define here file name. I call it new CZI, 16 planes, 3 channels. Basically, I will just convert this one to a CZI. And here now, what you would have to do is again using the context manager. And in this case, it's not open, but it's create CZI. You have to provide the file name, obviously. Exist, okay. If you set it to true, it will allow to overwrite. If you set it to false, it won't. And then basically here you have this CZI document and _w for writing. And now what you can do here is write large CZIs by iterating over the dimensions you want to write. In this case, we want to write Z planes and channels. So I iterate over the Z planes and the channels. And again, you have to provide, or actually, to be honest, this is not correct anymore. If you don't provide that one here, it will implicitly edit. I forgot to update the notebook because that was a wish from my side. As I said, a plane has either the dimension y, x, and 1 or y, x, and 3. If you only provide y and x, it will assume it's a 1. But okay, This is correct or still correct and will still work. So here, basically, I extract the data from the test data set to have some pixel data on an array level. So this is my array 2D. And here now I write this array. Will be super quick. You see it did iterate over 48 different planes. Makes sense. 3 channels, 16 set planes. And then I opened the image in Zen and went to the split view, and I see, okay, those are the 3 channels. It opened easily in Zen. Perfect. What you can do now is you can make it more fancy and play around depending on what you want to achieve. What you can also do is you can write to a specific location within a bigger plane. Okay, again, yeah. Let's create a new CZI here. I call it new CZI set location. So what we do is, again here, we open a CZI for writing, then I read set planes. In this case, we use the same data set, but I only iterate over the 16 set planes. And then I write it back to a new CZI. And what I did here is basically I defined a starting position, x = 0 or x start equals 0. And in the process of writing, I always shifted it by 512 pixels just for fun. So here you see 16 set planes. And then if you open it in Zen, now you have, instead of having 16 set planes, it will place all those images side by side. Why? Because we provided here location, and here we said x start 0. So it will be 0, 0, 512, 0, and so on and so forth. And that's it. libc_ZI read-write under the hood will create all the correct meta information for you. You don't have to specify this all by hand. You can see, you can open it directly in our Zen software. You could also open it somewhere else if you want. So this is writing to different locations. Okay, there's more. What you can also do is writing to different scenes. Scenes are, as I said, different or physically separated regions where you can have one or more images. So a single image or tile images as part of a scene. So here now I do a little playing around. I create basically a grid of different locations. 16 different locations. And now I do the same. Define a file name. I open my CZI for writing, which I want to create. I read from my example data set. Again, the set planes. And now I write the individual set planes to a channel and to different scenes. Basically, I read set planes, but I write it as scenes to the grid location. And here now you see the result. I have 16 different scenes physically separated. If you would open it in Zen, it would have a scene slider with 16 entries. Okay, so that means basically you have a lot of flexibility how to read data and how to write data and also rearrange it. Obviously, in most cases, you will probably, maybe you want to do some processing, so you write it back in the same way you did read it. Read a plane, do your processing, write it back to where it came from. Will be a quite common use case. Okay, let's move on. What about metadata? Like how many time points and set planes you don't have to worry about. This will be all done automatically for you. Obviously, there are sometimes stuff that you probably want to write on your own. as I said here, it's automatically written. Some metadata you can explicitly write by the write metadata command. This also comes back to this one initial question. So currently here, the parameters you can write are a bit, yeah, let's say limited. So there are only a few. And those are the ones that you can set. So you can write the document title, the channel names, and also the scaling. And as I said, this list of parameters will be extended in the future. Here's an example. So again, we read the CZI with these 16 set planes. Open the document for writing. Write, and then we set a certain scaling. Let's do it. Very simple. I'm not sure if you can read it. Maybe we have to zoom in. I don't know if you can zoom in here, maybe a bit. And here you see 16 set slices, 0.1 micron, 0.1 micron in X and Y, and in Z 0.3 microns. In CZI, officially, internally, we use SE format. So scaling is length units, therefore meters. So you have to apply this factor here. Yeah, that's the way it is. But you see here, it opens in Zen correctly as a nice 3D stack with the correct scaling and can be easily visualized. So obviously here, I think this is straightforward. Document name and channel names you can define as you like. And now let's come to probably the way we use it mainly at Zeiss right now, at least in our team. And this is tiling larger images. And here it now where this library nicely works together with the Cset tile array. So basically the logic is, let's read the CZI, extract a certain chunk of it, a tile, by using the Cset tile library, or maybe in your case, something else, and do some processing, and then, yeah, create a new one. So first, I do the same as we did already in the Cset tile notebook here. I reuse this Gaussian function just for fun. Okay, and here now it's again the same code, so I don't have to go through that in detail. I define here how the new CZI should be called. This is the original one. I create my tiler by providing the required parameters, and then I create the tiles. And now what you can do is you can open the CZI for reading and writing in parallel. What we do not allow as of today is basically reading and writing the same CZI. As I said, we start with the simple use cases. So open the one for reading, tile the image using the Cset tile package, then use the computed tiles as our I parameters, do your processing, write the new tiles back into a new CZI. So, and this now is what you can see here. I open for reading, I open for writing. Here I have my tiles, and now here I read a specific tile from my original image by using this RI parameter, which we just discussed a couple of minutes ago. Very simple. You just have to take the tiles from your loop and plug it in. Therefore, you only read that part of the original CZI, even if it's a really big one. Here you do the processing. In this case, it's a Gaussian filter, could be your deep neural network. You will see that at the very end of that session. And yeah, here then I write the new processed tile into the new CZI. And I can use the same parameters, just tile RI X and Y. So I just need the top left, because width and height are basically, yeah, defined by the image itself. So let's run it and see how it looks. Here you see it has 4 different tiles created and 4 different process tiles. And now here it's again this visualization of the tiles which you already know from the other one. And this image here, the processed image, is again now a processed bigger tile image, which you can read and send and do whatever you want, use for every workflow you have in mind. So the important part is not the visualization, but basically this idea. You open something to read and to write at the same time. And based on your application, how much you need or you can read at once, you read out a certain ROI, maybe with the help of the tiling package or something else. You do your processing and then you write back the stuff to the new Cset. So you only have to process or to deal with this smaller image. I see a little question. Let me read it. So is there a way to have an extra border when reading so that we're not affecting by border conditions? I'm not sure if I understand that correctly. Jean-Yves, do you mind? Maybe we, I don't know, send some emails, or you can obviously also speak. Feel free to speak up.
Hello, Sebastian. Thank you so
Hi.
much. The one thing I was thinking of is that, for instance, when you take a small tile and filter it with an aggressive Gaussian filter, the pixels on the border of the tile are going to be like probably average with black.
Okay, I know what. So if you use our tiling library, obviously you have this minimum border width. So if you use that one and you specify a border width, then the inner region of a tile will be basically, you have to set it big enough in that case. But this is only in conjunction with the with our Cset tile library here. On that level, it's really up to you. So you can do it as you like. You can use our tiling, where you can have this extra border, which basically can be used to make the processing nice, but will not end up in your actual image. Or you do something else.
Awesome. Thank you very much.
It's a pleasure, no problem. Okay, so that is it from our Cset tile, PyLib Cset read-write library. And now let's jump to the next one, the Cset model. Okay, I still have half an hour that I think will be a good fit. So what we also learned over the last years is, again, focus on AI applications. Wait a second. In the AI business, so to say, at least for me, it's pretty clear. There's always, you have to think about, where do I do my training? How do I do it? And then once I have my training done, I have a trained model, for instance, for segmentation. And then that model can be used in typically a different software as part of maybe an image analysis workflow to count cells, something like this. So, and that means basically you can separate the training software from the software where you use your model. That is very useful, especially from the perspective of software development. We call it separation of concerns, easier to maintain 2 pieces of software, not like one big monster that does everything. Nevertheless, you need to exchange the model. And here again, we said it doesn't make sense if everybody in Zeiss is using a different format. So let's create not our own new model format, but let's create a unified way to package machine learning models, including some meta information, into something that then can be exchanged between different parts in our software ecosystem easily, because everybody is using the same. And here the same logic applies. This is not a big secret. there's no magic in it. For instance, if we use TensorFlow for training, the model itself will be still the TensorFlow model. We just add some meta information and basically package it. I will show you this. Also, if you are interested, here you can read all the specification, but I think I will directly go to the GitHub repository. And here we have to go to this. I have to find it. Give me a second. Wait, Sebi 6. Okay. GitHub. I lost overview about my open tabs here. It's in the workshop information. Here I go to the Cset model, library, and now I go here to workshop. Here you find basically also all the information we just discussed. Scroll a bit down, Cset model package, and then here you click on segmentation. Again, it will open a Colab notebook. Oops, it's a bit big. Runtime. Do I have still sessions running? Terminate. Okay, so let's make sure that we use here the GPU runtime because we do a little training of a neural network. Okay, first thing here, you install the Cset model. Straightforward. Run the pip stuff. I will also install here the ONNX runtime to execute the model in the end. Little side note, we at Zeiss, whenever possible, for execution of a model, we use the ONNX format. It's way easier to manage in terms of GPU memory, in our opinion, compared to TensorFlow. Or we use PyTorch. Nevertheless, to execute it, mainly ONNX. Okay, it's doing all that stuff here, not so exciting. Takes a bit longer. There's more stuff to here. I want to get rid of some warnings. If you deal with TensorFlow, one or the other might know this. So, and here now we do our import, and here you see those tools. Cset model metadata, legacy metadata, default converter, and some transforms. I will come to that later. We import that stuff. And here I want to minimize some TensorFlow warnings. In this case, we are using TensorFlow 2.8, but it works with, I think, quite a range of TensorFlow versions. I don't think it works with TensorFlow 1. Okay, here now again, we download some data from our GitHub repository. And here, it's a little disclaimer. This little training pipeline is just an example. It's not meant to represent a nice and optimized training pipeline for a really cool model. It's just to show the principle. So we download the data from our GitHub page. Okay, it worked, nice. Yeah, here we need some helper functions, basically to read the original images and the mask images. This is what the sample data are. Some images of fluorescent nuclei and some mask image. And now we basically create our data sets for training. So sample images, sample masks. I just click through that. That's not the interesting part, but you can try it out later. We normalize the images, okay. And here, yeah, converted to this TensorFlow 1 hot stuff that is required. You can read it up here. I'm not going into that. That's not the important part of the notebook. Last thing here, now we define a TensorFlow dataset, which we can use for training. Here, this is our world famous segmentation model with exactly 2 layers. You can make this much more fancy, obviously, but it's a model. Now let's run a training with 25 epochs. This is the part where you are the experts. Here you can do really what you want, make a really nice model that serves your purpose. And here now we have to wait probably a bit. Let's see, did I switch to GPU? I think so. Yeah, okay. Won't be too long. And you see at least the numbers are changing a bit here, the loss function. That's not the point. What I want to show you is I want to have this trained model at the end. And here a little side note, a trained model can be created in a Jupyter notebook, but also obviously at Zeiss, we create trained models on our Appear platform. But we also use internally exactly this format, and you will see it in a second. Okay, training is done. Let's see how the results look. Here I just plot some image prediction, and that was the actual mask. Yeah, I mean, okay, it's for the sake of the principle, but you see it seems to work. So now the interesting part stuff. So now what you can do is you can easily package the trained model into this specific format that we call Cset ANN, car size artificial neural network, with these public specification. And what you have to do now is define the model data. So what do you have to define? Obviously, input shape, output shape, then the type of the model. In this case, it's single class semantic segmentation. There's more stuff. Multiple class semantic segmentation, regression, and so on and so forth. It's all in the specs. This notebook is only single class semantic segmentation. You have to put in the classes. So there's a background class and the nucleus class. A model name, and here define the overlap that is required by that model. In this case, we said only 8 pixels. Okay, then you create the model spec from that model metadata. If you use older versions of Zen, you can also create legacy models. They have slightly different specifications. You can read it up. And here, if you want, you can define pre-processing layers if you want to. Those are the model metadata based on the specification. And now we perform the export. So basically, what you have to do is now you take this default converter and convert from model spec. Model spec we just defined, output file path, then the name of the file, the spatial dimensions, input sites, and the pre-processing layer, which you can add if you want. Same works also for legacy. So let's try it out. Where did we stop here? We define the model metadata. Okay, that worked. Now we do the conversion to the Cset ANN. In case of older Zen versions, here the legacy stuff is also possible. You will see it here in a second. And that's basically it. Here, those are the metadata again as the JSON format, because what you can do is now is you can take that one here and read it directly into the Zen software or older Zen softwares, but you can also read it anywhere else. So here is a little bit an explanation about the model metadata, how it will be stored. Here you see what we created. Single class segmentation, background, nucleus, input shape, output shape from JSON, and so on and so forth. So those metadata can not only be defined like I did it here, but also from a JSON file. This is shown here. Clack, clack. You saved it. Here, model specification JSON can be also used. That's basically already it. So train the model you like, and at the very end, you can then read it in the software that you like. I saw a question. Wait a second. Is the Cset model? I assume you mean, is the Cset ANN format compatible with the bioimage model specs? Because the Cset model is just the name of the package. To be honest, I don't think it is directly compatible, because as in so many cases, it's not exactly the same specification. by itself, obviously Onyx, TensorFlow, and so on and so forth, I don't see a reason why it should not work in the bioimage model spec. So what we could think about, and this is also an invitation to some of you, this is open. We could create other converters, convert to bioimage, whatever. Why not? But right now, I think it will not work out of the box. But as I said, it's not a proprietary model format. It's just the way we package it with the metadata used in all of our software platforms. And that's the way it currently is. So I think it would be possible, but I don't think it works out of the box. But to demonstrate that this is useful, maybe also outside the context of Zen, I created two more little things here. For instance, imagine now you trained a model on our Appear platform, and I come to, maybe I spend 1 or 2 minutes to show this to you. So I'm not sure if all of you have seen it. Appear is basically a cloud-based processing platform with a focus on image processing. You can create workflows by combining individual Docker containers. This is one part. The other part that I'm now talking here about is the so-called Appear ML part. In Appear ML, you can train deep neural networks for segmentation without coding a single line. All you have to do is basically do something like this. I go back, I can also upload some data, go to the annotation viewer. Here you see an image. You can have more than one image. You can define some classes, and you can do what you can do in most of those softwares. Here you can label some structures and say this is a cell nucleus, and you can label here some background. And the cool thing on Appear is labeling is very simple. As probably most of you know, what's the hardest place for the network to learn information from? Exactly here, those regions where basically the cell nucleus would end and the cell starts. So this is about label-free cell nucleus segmentation, because by labeling stuff on top with background, it automatically gets cut out. See, and this is very easy to pixel precise then label the edges. And you don't have to label the whole images. Stuff you are not labeling is just discarded. So what we encourage people is rather label a few objects and do more operations and label on more images, instead of spending a day to label every individual nuclei, because it doesn't really help. Later on, you press the train button, that's it, you wait. And then at a certain point here, you get an email, training is done. It is, by the way, a quite fancy unit, a so-called efficient net that is trained. And if you go in here to the training results, you have all the information you need. You can also access the raw model, but more useful in our case, you just press here download machine learning model and you press legacy or new model. And what you will get is a Cset ANN file. And now you might say, Zen is cool, but my software is even cooler. Maybe. You could still use Appear and the CNN file if you, if you follow those instructions here. Imagine you did a training on Appear. Now you have the Cset ANN, but you wanted to use it in your own Python software. Does it work? Sure, it does. It's an open format. Here I import a little helper script to run an inference with an Onyx model, because as I said, we use Onyx. For training, TensorFlow, or already in some cases PyTorch, maybe in the future only PyTorch, who knows? But then we save it in the Onyx format, because especially in .NET, Onyx runs out of the box and we don't even need Python to do that. Therefore, Onyx is a very nice format. So here, I read some images and I import this Onyx inferencer. Here is my prediction function. Okay, and now here all I need to do now is I take this default converter function from our model package and unpack the model. So you only have to provide the file path to the Cset CNN file and the target. Where should it be stored? It's very simple here. And here you can create the temporary path so that you only basically unpack it, because Cset CNN is actually nothing else than a zip file. Okay, with a temporary file, unpack the model, read out the model parameters, for instance, the shape, do the prediction. Here you see model type, single class segmentation, input shape, output shape, model ID. So all of our models have a unique ID. This is important for model versioning, so you can't mix it up. Even if the file name is the same, the ID will be unique. Minimum overlap, classes, and then you can do whatever you want. In our case here, I will just plot the prediction results to show you that it works. Oops, no, what did I do? Did I forget to press something? It used to work. Shame on me. Index out of range. Sorry, I have to check. Okay, I hope you believe me. You can easily do the prediction and then plot it. It's, I think, just here. Okay. Length sample images. Okay, I have to check. Sorry for that. I will fix it as soon as I find time. That's always the case in live workshops. One thing won't work. I'm wondering if I missed some cell. Let me quickly check. I don't think so. Probably a mistake on our side. Nevertheless, what you can easily do is also train models on a peer, for instance. Take the Cset ANN model and then, oh, it works for you. Okay, interesting. I think I had this once, and it had to do something with scikit image import that sometimes didn't work. Okay, so we trust then in this case Kai. Thank you for typing this. So saves me some headache. I still have to probably find out why it doesn't work. Interesting. Whatever. Nothing is perfect. So and now at the very end, this is my last example. I will showcase a little bit this, I think, more, let's say, tangible example. In order to do so, please go to the following repository, Napari Cset ANN segment. You can also find it in the pre-read. A little disclaimer at the very beginning. It's still experimental. Here's a little animation of what you can do. Train on a peer. Obviously, this is not in Napari, but you train on a peer. Yeah, okay, that's fine. You download your model, you save it, and then you run it in Napari. And this, at the very last minutes, I will show to you, hopefully live. So fingers crossed. Also here, feel free to give feedback to this plugin. We are not like professional Napari plugin writers, but we did our best. We did it, I think, before Christmas. I said, let's have before Christmas a little internal hackathon. Let's write a little Napari plugin. And actually, it worked quite well. So what is the main function of that plugin? Basically, it has, okay, obviously some UI elements, but what it does is it implements a function to read the Cset ANN directly, as we just showed, by unpacking it. So the idea is you train a simple model on a peer, and then you want to use it in a Napari to do segmentation, or I don't know, something else. How do we do this? Try it out with the plugin. And basically, the main function is basically here the segmentation. We are not going to discuss here the details, but in principle, it's using the same logic as I showed you. It's reading an array, tiling it using the Cset tile library, unpacking the Cset ANN, could be also something else, and then basically using the model to predict the segmentation tile by tile and creating this and creating a new image out of it. And this plugin should work for basically n-dimensional images. The magic is all into this prediction function, where it basically loops over all images that you have, or dimensions that you have, extracting a 2D plane and then tiling it and putting it back together. So let's run it. Napari. I hope this works as well. So when I last tested it, it did work. So this is Napari, I think all of you know. So I open a CZI image. Here, this one. Yeah, a little bit, the auto scale function could be improved, I would say. This is our image. It's too big to be segmented at once. And now we start our plugin. Oh, I forgot to wait. I must install. I'm in the wrong environment. My mistake. So dann here pip install e. So I install the plugin. It's not on the plugin hub yet. I was not brave enough to publish it, I admit, because I didn't trust my own coding skills yet. But we might do so. If you tell me you like it, we can surely talk about it. Maybe then I will publish it and not putting it as an official Zeiss thing. Let's see. Okay, open files. Again here, so it looks nicer, a bit scaling. Okay, and now plugin. Here, Napari Cset CNN segment. Should show up here on the right-hand side in a second. Here it is. And here, basically, you have this button, select file. And now you go to the place where we downloaded the file from, in my case, from the Appear platform. Here, PGC 20X nucleus detector. You open it. Here you can adjust the overlap if you want to play around a bit. You can also reload the overlap that was in the model metadata. Here you can select the image layer. In our case, it's simple. There is only one. And wait, maybe I make it a bit smaller so you can see the console. And now you press here segment image layer. And now here you see it will create 20 tiles and doing the prediction one after the other. And I'm sure this can be done a lot better. This is just an example. And then it will show the output as labels. And it's not perfect in every case, especially if the nuclei are more or less overlapping, then it has a hard time. Yes, this is why we work on instant segmentation. But now you're basically free to do whatever you want. You can use other Napari plugins to do measurements, so on and so forth. Really up to you. But here we made use of the styling library and also of our CZANN package. Okay, and last but not least, there is one thing I also want to mention, and this is, wait, I have to Cset model library. I just wanted to make one thing clear because I think it can be useful for you as well. Here's another CodeLog notebook for regression. So Cset model, the package itself, as I told you, is not only for segmentation models, but also for regression models. Here it's again kind of an example. Okay, I have to terminate the other session. Close. An example of how to train your own regression model. Regression means basically input image and output image. Regression could be, for instance, denoising. For instance, in Zen, we have AI-based denoising. So we have noise to void integrated in Zen. But the implementation itself, it's not limited to denoising. That means you can basically train your own regression model that can do any kind of transform and still use it in Zen using the denoising function. Maybe we should rename it at some point. So let's here again train a little model, do the import of the required libraries. And here you see the Cset model libraries. Download images again. I go a bit faster. To come to the important thing, I define my training data set. I normalize my images, define the data set. And here now, here's a regression model. Again, it's a simple model, but it's a model for regression. Okay. Totally up to you. Let's do the training. This will take a few seconds. Okay, one epoch. It used to be a bit far. Okay, no, only the first one took a while. Okay, let's see. So here, why I show this to you is you might want to train your own magic AI function that transforms the image or does some better denoising or whatsoever. You can do it, train it in your Jupyter notebook and still provide it to your users. Now I'm assuming that at least some of you will be working in image facilities. You can provide it to your users by just handing them over the Cset ANN and say, use it in your Zen software. That would work easily. Okay, yes, training worked. Let's see if it did something, input, predictions, ground truths. Yeah, okay, it's a simple model. But now we have a regression model. And this is basically it. It's a Cset ANN. And again, here you can provide with the help of some model data, you see regression, save it as Cset ANN. And last but not least, now you have to at least once see Zen software. Here I open an image, here, whatever, this one. That's the original image. And here, this is my simply kidney regression model, which I just imported before the session. Here, remember here, simply kidney regression model. Trained totally outside of Zen, has nothing to do with Zen. All we did was following the model specification. So then here I take the image. Here I choose which GPU if I have more than one. Unfortunately, I have only a laptop, so I don't. You press apply, and that's it. This is super flexible. Yes, it's called denoising because it was initially developed for the noise to void function, but it can be used for any regression model. Okay, yeah, that was quite a lot. But I'm happy everything worked, especially, also not for me. This one thing why it doesn't work for me, I don't know, but when it worked for at least one person in the audience, then it's probably not the code, it's something else. I will dig deeper. But to summarize, so I hope you got a nice impression about those Python packages, Cset tile, unified, and I would say quite useful way to tile an array. Pylib Cset I read write, read and write Cset I images. Also parts of it, scenes, regions, different zoom levels, and writing it in case your downstream workflow would benefit from having a Cset I. And it's a nice file format. It's not the only one. And you can do what you want. But in our case, it's really useful because in our ecosystem, it ensures that the output of some AI processing can be basically used in our software seamlessly. And then we have the Cset model package. This is a unified way basically to package trained machine learning models, not only for segmentation, but also regression and some other stuff. You can read it in the specs. And this allows you to basically package your own models easily, including metadata and unique identifiers, use it in our Zen software. But it also works in a way that you can use a peer, create, you download the models and use it, for instance, in, as I showed you, in Napari to segment images. So it's really by no means limited to our own software solutions. Yeah, and that would be actually all I wanted to show you in this workshop. And yeah, please use the Colab notebooks. Then it would be, it's easy to basically play around a bit. Here's some, you found out why it didn't work. Scikit image that Kai and you know, my bet is, okay, yeah, probably. I will check that, that's a good hint. Because my gut feeling was it had to do something with Scikit image, but okay. Thank you for the remark. Okay, so are there any questions with respect to that? Otherwise, I mean, I will be around on the next days as well. And obviously you are all invited to listen to my talk in half an hour, which is a bit more on an abstract level about why it is beneficial in a bigger company to use Python packages to align internal business units, kind of. If you're interested in that story, it's a short talk, only 15 minutes or so. Feel free to join. Okay. If there are no direct questions anymore, then yeah, have fun and enjoy I2K. I can still remember as of today, the first one at the Amble, it was a blast. So hopefully in the future, one day in person again. Then bye.